All right, lesson 8, radioactive decay and decay equations. So the whole idea of radioactive decay is that nucleuses want to be stable. And what they're going to try to do is always try to either release something to become more stable or gain something to become more stable. So it's all about trying to become and joining this zone of stability. It's roughly equal to a 1-to-1 ratio of a proton and neutron, and it looks like it follows that for the first little bit, but then it kind of veers off a little bit, and it looks like it favors the number of neutrons compared to the number of protons. We start to get more neutrons and protons eventually in the zone of stability. All right, so here it says smaller nuclei are stable when the ratio is closer to 1-to-1. For larger nuclei, the stable neutron to proton is greater than 1, like we saw below. Carbon 12 is stable, while carbon 14 is known as a radioisotope, something that's a little bit less stable. So radioisotopes is an isotope that is unstable and undergoes radioactive decay. And another term that we often use is transmutation. This is when one element turns into another. So it releases something, and in that process will change the fact that it has so many protons. It'll either gain a proton or maybe lose a proton, and in that act shifts along the periodic table. So things that we always need to consider when we're looking at these types of reactions: did we conserve the number of nucleons? Is there a conservation of charge? Is the mass energy conserved? And is there a conservation of momentum? We'll talk about that a little bit more, but basically the first three for sure. All right, the first one we're going to talk about is alpha decay. So an alpha decay is when an element or a nucleus is so unstable that it's better off or more stable if it releases an alpha particle. And in this process, we'll release another, what we consider to be a daughter isotope. So we have a parent isotope, what we start with. It releases an alpha particle. If you notice this yellow section or orange section here, this right here is what's being removed as an alpha particle. So as a reminder, alpha particle is the same thing as a nucleus of a helium. So we're just going to take a look at this and kind of see how this would work out. And maybe we can try a quick example of an alpha decay, so we can actually try it with real numbers here. So let's go ahead and try something like, I'm just looking one up real quick. Here we go. Let's go ahead and say 226 number of nucleons and 88, and this ends up being radium. Releases, and in this case we'll give up 222.86, and this becomes radon, and in the process also gives up a alpha particle. We can say alpha or we can say helium, really doesn't matter. Okay, so what we're going to do, if you take a look at what's happening here, we have to look at the number of nucleons. Did we conserve nucleons? So here we have 226. Here we have 222 plus 4. So we have 226 before, 226 after. We have conserved nucleons. So we can say, yep, conservation of nucleons is confirmed. The next one is a charge. If we're talking about charge, quite often we're talking about the number of protons. So in this case, we had 88 protons, and at the end, we had 86 plus 2. We had 88 at the end as well. So we had 88 protons, and we turned it into 88 protons. So therefore, yes, we are conserving. In terms of momentum, we don't know exactly what's happening here, but we can make a prediction that if this particle was stationary, this parent particle was stationary, and an alpha particle decided to throw itself off to the side with some kind of speed, kind of like an explosion perhaps, we can make a prediction that most likely that this daughter product would also move. So one thing, in this case, we're not sure. There's maybe not enough information to kind of solve this one through. And mass energy, we'll talk about a little bit more. This has to do with that equation that we skipped over from the last topic. But in other words, there's going to be some release of energy, and in this case, we do see that. So really not quite sure, depending on this situation. Maybe more information would be needed. All right, so let's take a look at writing an alpha particle decay, alpha decay for polonium-216. So if you look at polonium on your data sheet, we see that polonium has a number of 84. So 84 would be the number down below. And once again, because it says 216 here, 216 is actually the number of nucleons for polonium. And polonium is PO. So if it released an alpha particle, it doesn't matter the order so much. I could say alpha first, followed by the other daughter product. But in this case, I'm going to be consistent with what I had above here. So I'm going to say 4,2 for the alpha particle here. And in order to figure out what else was the daughter product, we're going to use that same conservation that we used before. So I had 216 on top, number of nucleons. I have 4 at the end, which means there has to be 212 nucleons for whatever element this is. And to find the element, we're looking at 84, and we're taking away 2 because it has to be 84 on both sides. So in this case here, we're looking for element 82. So 82 here. And if you look at element 82, I do believe that to be lead. So that's PB. All right, so here we have a conservation. We check the number of nucleons, 216. At the end, there's 212 plus 4, 216. And at the bottom, the number of charge or protons, we had 84. And at the bottom, we have 82 plus 2, which is also 84. So that's good. So conservation confirmed. All right, so beta decay. There's 2 different types of beta decay that we'll be talking about. There's one that it emits an electron, and there's one that emits a positron. We're going to call this beta positive decay and beta negative decay. All right, so let's see what that looks like. So here it says a parent isotope, daughter isotope. We have a positive beta particle, and we have something known as neutrino. And it turns out that it was discovered, a neutrino was discovered because of this. They said, hey, momentum is not conserved. Somehow there's more electron. The electron's going up at an angle, but it should be going at a different angle. Why is this? And they discovered, using conservation of momentum, that there was a very small particle known as a neutrino, and they later discovered it at a location where they predicted it to be based off the conservation of momentum. So it's kind of a cool idea. All right, so beta positive, let's go ahead and take a look at an example for this. Let's see what I find here. So beta positive example, let's do something simple like a carbon. Let's go from carbon 10. So if a carbon 10 is my parent isotope, I'm going to say carbon. And because it's 10, and we know carbon is element number 6. And in this case here, it will produce a daughter isotope when it releases the beta particle and a neutrino. So I'm going to start with the second part and say, well, it's releasing a beta particle. And once again, I can do it one of 2 ways. I can say, well, the beta particle looks like this, kind of a fancy B. And technically, and I know I did it slightly different before, technically it has a 0 in terms of nucleons. Ooh, that's wrong. It has a 1. Nope, I was right. It has a 0 because there's no nucleons. It's a beta particle. In other words, a positron. And a positron is not a proton, not a neutron. But it does have a charge of 1. So I'm still going to put a 1 down below because technically a positron is a positive 1 charge. And I'm also going to follow that up with a neutrino, which kind of looks like a fancy V. And a neutrino is always a 0, 0, meaning there's no nucleons and there's also no charge. A neutrino is neutral. All right, so taking a look at the conservation of nucleons, we see 10 before, we see 0 after. So we have 10, 0, 0. So we're saying that this element should also have 10. Okay, pretty easy. And then we're looking at the bottom here. Well, we looked before, it had 6, and currently we have 1 after, so this thing must have 5. So therefore, we're jumping down the table, the periodic table, and we're seeing that it's going to give us, I think that is boron. Yeah, boron. So boron, it's just capital B, which is going to be a little bit confusing because we have the fancy B followed by boron. Okay, So in this case here, we have a conservation. So technically, this is more complicated than this process. Technically, there's something to do with beta decays. Sorry, not beta decays. Quarks in this process, that somehow we're converting a positive quark, proton. We're turning a proton into a neutron, which is a little bit confusing. So I'm going to quickly just do it. I think, do I have it later on? Yes. Okay. Never mind. I have it later on, so I'm not going to talk about it yet. Okay. So let's take a look. Take a look at the next one. Sorry, guys. Beta negative decay. So here we have a parent isotope releasing a daughter product, and then also a negative beta particle, an electron, and an antineutrino. So let's take a look at a quick example here. So let's do another carbon one. We're going to go to carbon 14 in this case. So I'm going to say carbon 14, and we know that carbon 14 has 6 protons because it's number 6 on our periodic table. I'm going to skip over the daughter product because I'm not quite sure what it is yet, and I'm going to have a negative beta. Okay, or beta negative. You can replace this with an electron too if you'd like. And we also have an antineutrino. So I'm going to just say antineutrino. So if you take a look at the charges, the nucleons on top, we had 14 before, and 0, 0, we must have 14 here. We had 6, but now we had -1. So in order to make it add up to 6, we need to make it 7, and then we end up giving ourselves nitrogen. So then we're left with a nitrogen 14, and a beta negative particle, and a antineutrino. An antineutrino is an antimatter particle to the neutrino. That's funny because now it says write an equation for carbon 14. Well, there, done. All right, so now we're going to quickly talk about quarks and how they're placed into this whole mess. Beta particle using neutrons and quarks, nucleons and quarks. So remember, this is talking about protons and neutrons. Oops, neutrons. So technically, a beta positive decay is when a proton turns into a neutron, releases a positron, and also a neutrino. So let's see what that would look like in this case. So we're going to write it out slightly different. We're going to say a proton, and that is a 1, 1, turns itself into a neutron, a 1, 0, then also releases a positron. Remember, the positron is a beta particle that's positive, so it's a 0, 1, and then a neutrino, which is just that fancy V, which is a 0, 0. All right, so the nucleons stay the same, 1, 1, 0, 0, and then the charge 1, 0, 1, 0. So that's all great. But remember, we mentioned earlier that a proton is actually made up of 2 ups and a down. So another way you can write this is by saying, well, an up, up, down, which has a 1, 1 charge, converts into a 1, 0, up, down, down, plus a beta positive and a neutrino. So what we're technically saying is, through this process of beta decay, positive beta decay, one of these ups turned itself into a down. So one up quark turned itself into a down. So an up quark changes into a down quark, which results in converting a proton into a neutron. And once again, a proton can't simply be a neutron without giving up a positive particle, because we have to conserve conservation of charge. All right, let's see what the next one looks like when we do beta negative decay. All right, in this case, a neutron, which is a 1, 0, 1 nucleon, 0 charge, or 0 protons, converts itself into a neutron, a 1, 1. Well, how can it do that? Well, we had neutral, now we have a positive. In order to do that, we must have had had a -1 for my beta particle. And in this case, also having an anti-neutrino. And the way I remember when it's a positive neutrino, when it's an anti-neutrino, the way I remember that is that this anti symbol kind of looks like the negative sign. So an electron and anti-neutrino always go together. A positron and a regular neutrino always go together. All right, and taking a look at it in terms of quarks, if we have a neutron, we said a neutron is an up, down, down, which has a 1, 0. We also have a proton, which is a 1, 1, which is an up, up, down. And then we can do our beta negative plus our anti-neutrino. And in this case here, instead of a up turning to a down, you're now having a down converting itself into a up quark. Okay, so it's just a down converts itself into an up, and in this process converts a neutron to a proton. All right, I'm going to skip over these examples just for time's sake. The last one I'm going to do here is gamma decay. Gamma decay does not produce transmutation. Gamma decay often happens alongside another type of decay. So sometimes when you see something followed by a gamma decay is basically a nucleus that's excited and releases some energy to be a little bit more stable. That's all that's happening through a gamma decay. So let's go ahead and try this example here. So it says that krypton 92. So we're going to say 92, krypton, Kr. Take a look at our periodic table. We see that krypton is number 36. Undergoes beta negative decay. So we're going to say undergoes, so follows this reaction. And let's do the beta part first. So I'm going to say 0, -1. Instead of putting a B, I'm going to change it up just so you guys can see it. Sometimes we'll see it as an electron. Because remember, a beta negative is an electron. It's the same thing. And remember that this also produces an anti-neutrino. So what is left behind? What is our daughter product in this case here? Well, if we had krypton, we released a -1. This must be a 37 instead. And we still have a 92 above. So if you take a look at your periodic table, we see element number 37 is rubidium, so it's Rb. And this is great because this is our beta negative, but then it says followed by a gamma decay. You could write this all out and then say plus gamma, which we're going to do in this case. We're just going to say plus a gamma. So this is only added when it states followed by a gamma decay. We can assume that it happens in most cases, but we're not going to add it unless it's stated in the question itself. So in this case, most cases, we can just say this is great, but once again, it says followed by a gamma decay, and that's why we're adding the gamma decay. And for charge and number of nucleons, we can say it's also a 0, 0. All right, so try the questions that follow in lesson 8 here. If you have any questions, please make sure you don't hesitate to email me. Yeah, and that's it.